Any questions? All right. Well, Sergey calls it an invariant talk. I call it a research report because it's really what it is. It's more like a good bunch of brain dumps from me. So thanks for being here. My name is Julien Vanegue. I work at Bloomberg as a security architect. Today my talk is about heap models for exploit systems. So half of the talk will be pretty much about reminding you guys what we're talking about, making sure we're on the same page. And the other half of the talk will be a little more formal or tentatively formal with the kind of insights I think I have gained by analyzing a lot of different heap allocators over the years. So how many of you have written heap overflow exploits before? Many. All right, excellent. So if there is anything wrong in what I say, please interrupt me right away. I'll be glad to be proven wrong on anything and always eager to improve. So interrupt me anytime. If you have questions during the talk, you feel free to actually ask them right away. You don't have to wait until the end. So let's get started. The big picture of this work is what I called 1 or 2 years ago the Automated Exploitation Grand Challenge. As you may all be familiar with, the security exploit is a way to basically take advantage of security vulnerability in a program, either to do untrusted code execution or to steal secret information, for example, private keys. And a bigger challenge, so a lot of these security exploits are written manually generally, or most 99.99% of the time. And for 0.01% of the time, people claim that they can sometimes automatically generate these exploits. I am highly skeptical of that in real world conditions. So this work is trying to understand how to basically resolve one of the problems that I set up in the Grand Challenge, which is a set of 11 problems that I believe are very hard to solve. So some of the problems are about how to specify what an exploit should do, how to generate input for the exploit, how to represent state space for the program under attack, how to explore concurrency scheduling, how to infer privilege separation and things like that. So it's not trivial at all. One of the problem, which is problem I of the Grand Challenge, is heap prediction. So, but how can you infer the state of the heap in a complex program? It's a really hard problem. Most people haven't really studied the problem at all. A lot of the research on heap analysis has been mostly for things such as shape analysis. Shape analysis is basically how to analyze the shape of data structures in the heap. For example, if those are linked lists, graphs, trees, acyclic, etc. We're not going to talk about that. My goal is not to do shape analysis. My goal is to see how we can predict the layout of the heap. So the layout of the heap, you'll see, is the state of various internal structures of the heap that can be useful for exploitation. Also, the heap can be non-deterministic. Sometimes the heap would act 90% in a certain way and 10% in another way. So it's very hard sometimes to come up with a semantic of the heap that reflects that. I'm not going to try to do this today. You can try to do this using things like Markov models or Bayesian network and stuff like that. I'm not going to do that today, but it's something I'm researching. However, it's going to be for future work. Okay, why is this an actually important problem to solve? First of all, because most research about heap exploit is very arcane, as I call it. It's like arcane knowledge that exploit writers actually come up with on the fly. They have a target and they try to find conditions under which the target can be exploited. This is one-off effort, usually exploit after exploit. Also, heap allocators are extremely different for each operating system. DL Douglas malloc on Linux is quite different from its successor ptmalloc, which basically add multi-thread support to DL malloc. On Windows, you have the Windows heap with things like the low fragmentation heap. I'm going to talk about this a little bit later. Say Firefox, you'd have gmalloc, which is one more different allocator. So is it really possible to come up with a generic heap reduction technique knowing that all these allocators are so different? That's what I try to solve. It's kind of an impossible problem. So don't blame me if I don't manage. But I think there are some good stuff to actually infer from that. My goal is really to try to formalize such technique and ideally write a tool that will be usable off the shelf. To do that, I'm still developing that tool. So from the evaluation side, you're going to be quite disappointed. However, we'll go through the details of what I've learned by analyzing the allocators. Just a few reminders. A few different vulnerabilities that people experience on the heap are heap-based buffer overflows. You guys are pretty much familiar with that. Heap-based buffer overflow, an attacker can typically override the adjacent memory chunk. So if there is any interesting data after the data to be overflowed, then the attacker will try to corrupt that. Maybe it's a function pointer, maybe it's some authentication flag, and so on and so forth. Double freeze, invalid freeze, sometimes it's possible to basically execute a primitive on the heap that will corrupt the heap. For example, if you try to free something twice, or if you try to free something that's not a heap chunk, then bad things can happen. Use after freeze are major class of vulnerabilities these days. It basically, especially in browsers, IE has been full of these in the last few years, not just IE, but also Chrome and Firefox. And basically, that would be when a pointer is freed prematurely, but there was a value of the pointer that's cached somewhere in a local variable, and this local variable gets used later on. And that's where you basically can manipulate data that is an inconsistent state. I'll give you a basic example of that later. One more class that's interesting is information disclosure. It's when typically you'd have an out-of-bound read, and the attacker will be able to read the content of the memory space. So not necessarily getting untrusted code execution, but reading data that it's not supposed to read, which is sometimes enough. For example, in the case of Heartbleed, if you read a private key in the memory, it's a big deal. So just really short intro. Heap overflow, obviously, there's malloc happening. There is some kind of mem copy happening, which is could be out of bound. For example, here you could have a short integer overflow that will basically lead to a heap overflow in mem copy. So what's interesting here is that what's after that chunk, right? Because you're going to overflow the chunk. So what's after it? Is there anything interesting after that? There is. What's the location of that chunk in the heap, and what's after that location? An invalid free, say you have some error condition, say on line 4 here, you'd have if y equals 0, it goes straight to n and it frees the result, but the result was supposed to be allocated here, so it goes straight to free, and you free an uninitialized value, so you would basically free a pointer of whatever value was in memory at that moment. That's a problem. People have been taking advantage of that. Similarly, what can you free with that? What's the location that can be abused, pointed by result? Use after free, several high-profile bugs like Aurora vulnerability when Google was hacked a few years back, 5 years back, and it was because of a use after free in IE6. Typically, you'd have a pointer that's mallocked. You may have a null check usually, and then it passes this to a function with certain input, and this function may free the pointer under some conditions, some obscure conditions that almost never happen, but sometimes it happens. And then you have this local value cached this PTR that would normally point to malloc, but because that was free, then PTR will basically point on freed memory that may have been reclaimed by another chunk later on. So that is typically what happens when you have a use after free, of course, in real life cases. So they're much more complicated, but it's just for the sake of putting everybody on the same page. Information disclosure, like Heartbleed, you'd receive something from the network, you'd get, say, a record header, and you'd malloc an output buffer. After that, you would basically copy something of a length that was provided by the user from the network, and even though you don't have a buffer overflow because you malloc the right thing, you may basically copy things that were after the intended data copy. And there, but when you send this back to the user will basically see data that was lying around in memory. And if that data was sensitive, then that's a problem. Also, this is very important to understand what was after this chunk, or what was as memory claimed by that malloc. Was this zeroed after it was freed, or if it was not, what was in there? And if it's copied and if it's not initialized, then that could be a problem. Like here, once you copy to the out buffer what was at buff plus size of rec for that length, then you got a bunch of uninitialized values that's going to be copied to out. So what was after that particular piece of data in the heap? All of that, just to say that trying to infer the location and the relative location of chunks in the heap is important for exploit writers, and usually critically important to get a successful exploit and like a reliable exploit and so on. One of the harness tests I created in my grand challenge is the following. So we'll go through that because it's kind of interesting to understand. Let's say you have the following small example where you have structures of type S1 and S2. I'm seeing that there is some missing curly brace here. I'm sorry. Is that true? Yes. Okay, so basically what happened here is that you've got a function that allocates a few of these structure S1 3 times, and you got a function that allocates structure S2 1 time. You got a function that frees a structure of type S1. You got a function that copy data in the structure, and basically the goal, where you want to reach is the point where you basically say print uint, just for the sake of understanding. And what you don't want to do is to fall into this case where you would basically copy some data in a pointer that was freed. So you wouldn't want to do, say, you wouldn't want to free that pointer and then try to go into that because you may crash the program. However, if you go into that, you may basically be able to influence the value of this flag. And if you manage to get this flag to 1, then when you satisfy this condition, you would basically go into the winning state. So one of the key to understand exploitability about this example is recycling of chunks. Recycling of chunks means when you free some structures, the chunks will in fact not be back to the heap, but it will be placed into a list of available chunk. And whenever you have an allocation to satisfy, if a structure would be the same size, in that case, S1 and S2 are of the same size. But if you reclaim the chunk by a structure of the same size, you basically may be able to take advantage of the fact that there were some certain values. For example, here, if you initialize that guy to 1, then if you reclaim P2, authenticated will become 1. So typically, a successful run would be to call the function in this order. You would like to allocate those structures, and then you'd like to free one of these structures, and then you'd like to reallocate a second structure. Because structure 2 is of the same size as structure 1, then the chunk that was pointed by P1A will now be pointed by P2. After that, you want to basically copy values into that stuff, and then you want to call the winning function. However, you don't want to call that function, or otherwise you're going to crash. So how do you automate finding of these heap worlds, as I call them? That's kind of a harness of the problem. How can you find automatically whether such a walk is possible to lead you to an exploitable state? So the allocator I've studied are the following. So Douglas malloc, it was up to glibc of 2006, and then ptmalloc was introduced in glibc. ptmalloc is pretty much dlmalloc with thread support. By thread support, I mean that you have the ability to have a separate heap per thread. You have the Windows heap. Windows heap, it's a very interesting piece of code because there are multiple allocators in a single process. You'd have something called the front-end allocator and the back-end allocator. And based on such or such condition, typically if you allocate at least 21 chunks of a given bucket size, it would switch to the other allocator. So that's kind of interesting when it comes to analyzing the heap automatically. Two other allocators I have not studied are gemalloc and any garbage collection. Well, I have studied them in a different context, but I'm not going to talk about them today. So today we're going to really focus on mostly dlmalloc, ptmalloc, and also I will hint on how to modify slightly the formalism to support Windows heap as well. Okay, so typically the algorithm of a heap allocator is as follows. First, if the last free chunk can be reused, it will be reused for the subsequent allocation. If it's not the case, it will basically try to find one free chunk in the free lists. There are several free lists. Usually, it depends on the allocator, but usually you have one free list per bucket size. So you have certain intervals of sizes, and a given allocation will try to look up a given list. Say if you make a malloc of 10, it will go into the first free list and say, okay, do I have a small chunk of at least 10 bytes that can satisfy this allocation? If so, it returns that one, it'll unlink it from the list, and it will mark the chunk as allocated. If it doesn't find this in the first list, it will try to go to the next list and say, okay, do I have a chunk that's slightly bigger because it's in the second list that can satisfy this allocation? If so, do the same thing. And it is going to go list after list like that. Also, if there are two free chunks in a row, say you need 32 bytes. However, you just have two free chunks in the list. One is 20 bytes and the other is 30 bytes. What it will do, it will coalesce the two chunks. It will unlink the chunk of 20 and a chunk of 30 bytes, make a chunk of 50 bytes, and put it in a different free list. Or actually, it will claim it for the allocation. It may even split it to the exact right side that it needs and put the remainder to some other free list. So that's typically the steps that are taken. And those steps are pretty much consistent across allocators, even though, of course, some implementation details change. Abstractly, that's what an allocator tries to do. If it doesn't manage to find any chunk in any free list, what it will do, it will extend the heap. On Linux, typically, you would call a system call BRK. BRK will extend the heap. It will basically bring the address of the heap, of the last address, the highest address of the heap will increase a little bit. So say you had the last, I'm just making that up. If you had the last allocation at 080483, 0, 0, 0, or yeah, so it will basically say, okay, now the highest address is 080481000. And then every time you will basically need to allocate more memory, it will try to do this algorithm, and if it doesn't manage, it will extend the heap, and the top chunk will be the chunk that is, at the top of the heap. So remember about that. The top chunk is quite important. Otherwise, it just returns an error, and then malloc returns null, realloc returns null, calloc returns null, and then the allocation just failed. So what we really try to do here is to define a transition system for the heap. So if you have an initial state for the heap, you start here, it's an empty heap. You may have, depending on what the program executes, you may have a transition. Say you do an allocation of 10 bytes, and here you do an allocation of 20 bytes, and here of 30 bytes. And then after that, you may do the second allocation, or you may do a free, or here you may do a free as well. In that case, you'd come back to the H1, B, H5. And based, each of the primitives of the heap perform the transition on the configuration of the heap. So empty heap, and then you perform two primitives on the heap, and it may cycle, it may go very deep. What's interesting though is that this transition system is only dependent on the primitive of the heap. You have a huge amount of operations happening in the program, and these totally do not influence the heap if you don't touch the heap. So you can kind of abstract what happened to the heap. Even though the program is complex, it might even be, say, Turing complete, it doesn't really matter, because what matters is what happened on the heap. And that's what we try to analyze right now. So the key ideas to be able to define what I call the semantic of the heap is to understand that there are two levels of semantics. One is the physical semantics. The physical semantic is the adjacency of chunks. So which chunk is adjacent to which other chunk? So in memory, there is a linear memory, and you say, okay, A is after B is after C. And then you have the logical semantic, which is how are the lists that I just mentioned multiple times, how are they populated? And they may be populated, and even if you're after another chunk in the list, it doesn't mean that you are physically after that chunk, because it depends on the size, right? Each list depends on the size of the chunk. So two adjacent chunks in the list will not be physically adjacent necessarily. If that makes sense. So this distinction is quite important, because when it comes to analyzing adjacency of chunks, the physical semantics is all that matters. You may take chunks from lists, put them in lists. This will never change the adjacency of chunks. It will just change the state of the chunks, whether they're allocated, whether they're freed. But it doesn't matter. The adjacency predicate, as I will define in a second, does not get influenced by whether you free or you malloc something directly. It may do so in certain conditions, which I will talk about. So that's the first insight. Second insight is obviously you'd have to model the semantic of the primitive of the heap, like free, realloc, alloc. I call them FRA in this. But also internal heap mechanisms should be defined. For example, and I came up with 3 different ones that are everywhere, omnipresent in the heap allocator implementation: coalesce, split, and expand. We'll talk about what these things are in a second. The goal is to reconcile the physical and the logical semantic of the heap. All right. Any questions so far? Am I being clear? Is it making any sense? Good. Okay. All right. We are entering a little bit more sensitive part of the talk. I hope I'm not losing too many people with these notations. These are nothing complicated, really. If you have any question about it, let me know. So formally, what are we talking about? Sorry. The heap, you can see it as a tuple. Let's call it a tuple. a set of lists, a set of orders, like two orders. One, I call it the capacity ordering, the other the granularity ordering, and those are orders on lists. The capacity ordering is which list has the most free chunks. So you'd have an order between lists, and this order depends on how many free chunks are in that list. The granularity ordering would be the size of chunks in that free list. So for example, I would say that a free list that has free chunks of 32 bytes, which is the minimal size usually, sometimes 16 bytes, sometimes 32 bytes. A free list that has chunks of 32 bytes is more granular than a free list that has, say, 128 bytes. So that's what I mean. And this is really hidden in the semantics I'm going to show. So if that confuses you, don't worry, just forget about it. What's really important, though, is the adjacency predicate. Adjacency predicate is you take two chunks, and if they're adjacent, this predicate is true. If they're not adjacent, predicate is false. Very simple. And additionally, there are two maps or functions, if you prefer to call them functions. It takes a list, and it returns how many chunks are allocated in that, how many chunks are allocated as in that list. So it's a bit abusing the language here because, in fact, there is no list of allocated chunks. There are just lists of free chunks. But basically, take it that way. How many chunks of the granularity of that list are allocated? This is how to interpret this one. This is the counter map for free chunks. So given a list of free chunks, how many chunks are there in that list? So these are kind of the basic block of semantic of the heap I'm trying to define here. Now, talking about heap primitives. If you remember, I tried to define a transition system that goes from heap configuration to heap configuration. And the transition system, the arrows, the transitions are basically one of these kinds. So every time a heap primitive is performed, whether it's a free, realloc, alloc, coalesce, split, extend, then you'll go from one heap configuration to another heap configuration. And typically, you would write it like that. So you take the input heap, say it would be H0, the empty heap, or hopefully it's not the empty heap if you do a free. But whatever heap configuration, you perform a free on pointer P, and you get a new heap configuration H prime. Similarly, if you realloc a pointer for size S, then it will basically give you a new heap configuration and a fresh pointer P2 that's of size S, at least. If you allocate a pointer of size S, similarly, it will take input heap, it will give you a new heap configuration and give you a pointer with size S at least. If you coalesce two chunks, P1 and P2, it would usually give you another heap configuration. You could say there is a P3 here, which is kind of the union of P1 and P2. I haven't displayed it here. If you split the two chunks, similarly, you'd have two chunks. I didn't write P1, P2, but if you split a chunk P at offset S, you'd have basically a chunk that starts at P and a chunk that starts at S at P plus S. And then expand, if you have a heap and you want to expand the heap, you have a new heap, and then the top chunk is P, where P is of size S at least. What's important as well to understand how the heap operates is the fitness algorithm. Fitness algorithm is basically how the heap allocator decides which chunk is the most fit to satisfy the next allocation. One way to define such fitness algorithm is that way. I just use the ML style syntax because it's easy. And you'd say, and I will use this particular fit function afterwards. So just try to understand the overall idea, but the detail of this implementation is not really important after this slide. So you'd have a fitness function. It takes all the list of the heap, or it could take the whole heap if you like, and it takes a certain size. So what it does, it says, okay, match the list. If there is no list in that list, then nothing fits, right? Bottom means error. I'm not finding anything. However, if there is a thing in the list, say there is a top, a head and tail, that would be just one list, and then there would be the rest of the lists. Then what I'm trying to do here is I will try to find what is a matching chunk in that particular list. So here I implemented one particular fitness function, which is a best fit. Best fit will try to minimize the defects, try to minimize the extra memory in that chunk. So let's say I'm trying to make a best fit on the current list for size. Then what will it do? It will parse a list, and it will check. Actually, that won't parse a list. Find fit is first it goes here. So it takes a list and it goes recursively for one chunk after the other, and it says, okay, if the list is finished, then the candidate I recorded so far will be my candidate fit chunk. Otherwise, if there is still a certain amount of chunks in the list, I will try to see whether cure chunk, a cure memory unit will be a best fit. So it calls the choice function, and choice function, remember, is a best here. I gave best as a continuation. So it will call this particular best fit function with the current chunk and the size I'm trying to satisfy, and the best candidate I had so far. And at the beginning, the best candidate I had is nothing. I didn't have any candidate. So obviously, and I should have an extra condition here, if cand is bottom, then obviously cure will be a better fit than bottom. So it will return cure. Otherwise, if cand is a better fit than cure, it will return cand. And so it will iterate over the list like this. It will actually iterate over the list like this here, recursively. If I have nothing else in the list, I will just return my best candidate so far. Otherwise, I'll keep recursing on find fit, popping each element of the list one after the other. So anyway, just to tell you that this is a way to just define a fitness function in the very simple syntax, the meta-language style syntax. Now, what's interesting is if I don't find anything in the current list, I try to iterate over here. So right here is res, the result is nothing. Right? What I'm going to try to do is to fit into the next list. So if the right bucket corresponds to a certain list, but that certain list has no free chunk, I'm going to try to find a match in the next list. And I do this over and over until I actually find something that suits my allocation. So one way of thinking of fitness function is just, passing the list to see what chunks satisfy my fitness algorithm. Best fit is one of them, minimizing defects, minimizing a memory footprint, say trying to avoid fragmenting the heap as much as possible. You could replace that by the first fit. As soon as you find a chunk that's okay, you return that chunk. That I just did the best fit because it's a little more elaborate, and otherwise it would be just return, and you wouldn't have any of that passing. So I wanted to show you a bit more complex example. Right. Now you understand the fitness algorithm, hopefully. Fit is what matters, okay? Fit returns what list will be able to satisfy this allocation. So you give me the list of lists, and you give me what size you're trying to allocate, and I will return you what list is going to be able to satisfy that chunk. Can you guys see that? Yes, it's a bit small. I'll try to summarize. So this fit function we just talked about, I use it here, I use it here, use it here, use it here. This is very basic heap semantic you would expect. And what I track in this particular semantic is a set of counters. The counters is how many chunks are allocated, those two maps I mentioned previously. There is the allocation map, the allocated map, and there is a free map. So say you want a free P. and P is of size X. So what list was actually fitting X? If that list was L1, what's going to happen is that when I free it, L1 will have one more allocatable chunk and one less free chunk. If I want to do a malloc of X, I will find which list fit X. Once I have that list L1, I'm going to say that there's one less free chunk and one more allocated chunk. I say allocatable, sorry, that was allocated. Is there a typo here? Realloc, similarly, we'll try to realloc pointer P1 with the size X plus E, X being the original size and E the extension size. So that's why I said here size P is X, and then X would fit L1 and X plus E will fit L2. So what happened here is that this particular L1 list will get one new free chunk and this one will have one less. That's what I say here. I say, okay, there will be one less allocated chunk for in list 1, one more free chunk in list 1, one more allocated chunk in list 2, one less free chunk in list 1. In list 2, sorry. So it's just basically updating counters, nothing, no rocket science at all. But really this is not enough to predict the layout of the heap. As you can see, there is no adjacency going on here for good reason, because adjacency only depends on how you extend the heap, right? The first time you obtain the address of a heap or of a heap chunk, then it's when you actually extend that heap for making the top chunk higher than it used to be. So the real semantics, the real interesting part of that is those three rules. The coalesce rule says, okay, I have two chunks, P1 and P2, and I want to coalesce them. I want to make a big chunk, P3, out of those two. So say P1 has size X1, P2 has size X2, X1 fits into L1, X2 fits into L2, X3 fits into L3. What's going to happen is that those two free lists will get one less chunk, and these free lists will get one extra chunk because we coalesced one chunk as P3, and the size of P3 is the size of P1 plus the size of P2. That's why we have one chunk in this guy. Similarly, well, inversely, I should say, when you split a chunk, say you have a chunk P and you want to split it at offset O, you will split it into two different chunks, P1 and P2, and you'll have one less free chunk in the list that fits the size of P. The size of P, if the size of P is X, and the list that fits X is L2, then at the end of the day, in L2 you will have one more free chunk, and in L3 you'll have one more free chunk, in L1 you'll have one less free chunk. So when you had P, which was originally in the list L1, you'll take it away from the list, and then you'll add those two chunks, P1 in that list and P2 in that list. So you basically create chunk. Here, that's interesting. That's our adjacency predicate. So here, when you split a chunk, you know that P1 and P2 are adjacent because they were part of the same chunk. So you just cut that chunk into two. So P1 and P2 are adjacent. Here, you know they're adjacent. Another way to know that you have adjacent chunk is when you had a top chunk. So here we'll say top before and top after. Say you want to extend the heap for size S to make a new chunk P. Then if the list that fit S, sorry, not X, but S, the list that fit X is L, then the list L will get one more allocated chunk. Should that be one more free chunk? Yeah, that's not a typo, I'm sorry. You'll get one more free chunk in this particular list, and the new top chunk will become the new chunk you extended, And obviously, whatever was the top chunk before will be adjacent to the new top chunk. So that's another way to figure out that you have adjacency. And that's, I think, this is key, that only those two rules are affecting adjacency of the heap. Because allocation, free, reallocation, all these things, those are logical operations. Those are not physical operations. This is a physical operation. Extend is a physical operation. Split is a physical operation. Nothing else is a physical operation. So when you try to predict the state of the heap, keep in mind that the adjacency of the chunks only depend on how you extend the heap and how you split chunks in the heap. Everything else is housekeeping. It's just how you maintain your lists, how full are your lists. So if you maintain counters of your lists, you know how many heap chunks are in each of these lists. Then you'll know whether a list is going to be capable of fitting a particular chunk. If that's the case, then you're going to take one of these chunks out of the list, and you will decrement the counter. If that's not the case, you'll take the next list and see if you have one chunk that can satisfy. But these will not change the adjacency of the chunks, because chunks already exist. They're just in the free list. They will be reused sometime. But the adjacency of those chunks will not change. OK. Obviously, I passed on a lot of implementation details here. My goal was really to give you an overview of the thinking or the insights I think I gained by looking at all these implementations. And there are lots of details I didn't talk about. Obviously, the calculus as I presented it here is not entirely describing how the heap works. For example, I didn't talk about metadata. And there is a reason why I didn't talk about metadata, because even though most of the heap exploits nowadays use metadata corruption to, say, write anywhere, whatever they want in the address space, most metadata gets protected over time. In the last 10 years, 15 years ago, no metadata was protected. People could corrupt before chunk and the next chunk, and they would say, okay, now you're gonna write to the address in the next pointer that I supplied during an overflow, and that was enough to basically overflow an heap exploit. Nowadays in glibc, I was counting just a few days ago how many consistency checks are there. There are a lot of consistency checks in the heap allocator. A lot of them, and several people in the last 10 years, 15 years, I should say, have studied all kinds of ways to corrupt metadata to exploit heap overflows. And my take on this is, if metadata override is not dead yet, it will be soon. So don't rely on that anymore, because this will, this is not how you write reliable exploits. What matters is which user data is adjacent to which other user data. So what's inside that chunk? Don't try to take advantage of the metadata aligned in the heap. Try to see where are the function pointers in the heap? Where are the authentication flags in the heap? Try to get those chunks just after whatever you can override. Try to override a function pointer. Try to override an authenticated flag. Try to override a virtual table function pointer. That's how Aurora worked for use after freeze. That's how a lot of different exploits worked, actually. So really, the trend, it's been a little while already, at least 5 years, even more, I should say. Maybe that'd be 10 years. But more and more, metadata exploitation is going away. What matters is where the chunks are located, where the adjacency of chunk, and whether you can predict the layout of the heap. After all, if you could just use metadata, why bother? Because any chunk has a header with metadata in it, so any chunk would make it. However, protections are increasing on the metadata, and we'll reach a point very soon that it's not possible anymore to use metadata for exploitation. Pitfalls of this small analysis. I just described a single heap. In fact, in systems, you have multiple heaps sometimes. I pretend that this calculus can be adapted fairly easily to deal with multiple heaps. Just when you have a list of lists, you'd have a list of lists, and then you'd have a heap selector function that would basically say, okay, you're acting on that list of lists or this other list of lists, depending on which heap you're using. So if you're in one thread, you know you'd use that heap. If you're in another thread, you'd use the other heap. And in fact, it's not possible, I believe, to infer the layout of one heap based on another heap, because all heaps are pretty much independent. One heap is independent from the other. So this analysis I presented is really intra-heap. For a given heap, how you infer the layout of the heap. Even more vicious. Sometimes you have two heaps that are in the same thread. So you'd have a front-end allocator and a back-end allocator. I mentioned low fragmentation heap. I've devised the same whole semantic for the low fragmentation heap, which is a little bit different. But I didn't have time to actually explain all of that. So here you have something called an activation heuristic, where usually you would use a front-end allocator, which has just one single list, just one list, whole list of 3 chunks, and you will try to satisfy your allocation by one of the chunk of that list. But after a certain amount of allocations for a given bucket size, you'd switch to a back-end implementation of the allocator, which is a low fragmentation heap, where you'd have one list per bucket, which is why they call it low fragmentation. So I did not explain the activation heuristic here, even though if you had 2 of these inference rules acting in parallel, you could switch from one to the other based on whether or not the low fragmentation heap was activated for a given bucket size. So also this multiple heap allocator is not so much of a showstopper. You just need to know that it's there. I use lists. Some allocators implementation like gmalloc use RS, so you cannot translate my small frax calculus to gmalloc as it. You'd need to change it a little bit. I think you can make it much simpler if you deal with arrays, but I haven't really done it, so I don't want to say more about that. And finally, I didn't talk about non-determinism. As I said, you have some implementations like diehard. Diehard would it's a secure heap allocator that would randomize the heap. It will do randomized decisions on the fitness algorithm. So it's it's not a deterministic fitness function. It's a non-deterministic fitness function. Similarly, in the low fragmentation heap, since Windows 8, there was a non-determinism introduced where certain lists or each list in a low fragmentation heap is represented by something called a subsegment. If a subsegment becomes full at 80%, it will create a new subsegment, just to make sure that you can't fill a complete subsegment to have full control over the layout of that subsegment. So that's another way where the pitfall of that. To sum up, heap allocator implementation analysis is really hard, but if you there are some common functionalities like split coalesced, the list-based abstraction. Metadata corruption is dead or will be soon. So focus on what I call location guided abstraction, because I believe that's what will work or still work and will work in the future. I'm still implementing this whole thing. I may release my tool from some time. I will give a follow-up talk at SummerCon in New York in about 2 months from now. Hope to see you there. I'm happy to take questions. Thank you.